Welcome back. In the following section we are going to look at hardware and software. So in the previous section we looked at the need for information systems and how it affects our daily lives, as well as how do companies use information systems and what types are available. And now we're going to look at more technical aspects such as hardware and software. As part of the overview, it's important that organizations look at the costs associated with computer hardware and software, because ultimately they would need to give out money and hopefully in return they would improve their worker productivity, increase their revenue, reduce costs, and provide a better customer service. So if all of these are present, you're going to achieve your goals of your organization easier and therefore make more money. Now, we're going to start off by looking at some of the components that we find within most of the computer systems. We're going to differentiate between single user and multi-user computers, define a few terms such as green computing, data centers, and then we're going to move over and talk about different types of software. So what do we mean with software? What is available for different categories? For example, if we talk about spheres of influence for individuals, for work groups, as well as for enterprises. And then we're also going to look at the basics of programming languages and some basic software issues that we could experience. What happens if there are software bugs available or present within an application? So let's start off by distinguishing between hardware and software. Hardware can be defined as the physical components that allows us to perform input, processing, storage and output. So whenever you work on a computer, remember we've spoken about the system components, which consisted of input, processing, output, as well as feedback. So at this stage we're going to continue talking about that, but bringing the physical hardware components. At the later stage we're going to move over to software. Now software are all the programs that help us to run the computer as well as to perform our daily activities and tasks. So you might ask, why do we need to know about hardware and software? If you're not a technical person, is there really a need for you to know this? And the answer unfortunately is yes. In order for you to be effective in a company, you need to know what is available, what are the limitations, what can you expect from particular devices, and if you in a more financial unit or division, you would need to know what it's going to cost your company in order to have software and hardware upgrades in the near future. So let's start off by looking at hardware. So what is hardware? Hardware consists of a few components. So we can actually go and subcategorize it and divide it into input, processing, data storage, as well as output. And we're going to look at each one of these in a little more detail. So if we look at the screen here in front of us, we see an example of a basic computer system. You've got a screen, you've got speakers, you've got a keyboard, a mouse, and you've got your actual computer or system unit. So the next section will actually talk about these aspects and categorize them as either input, processing, data storage, or output. Now let's look at the components that we typically find within the hardware system. In order for a computer to function, we need to have a system unit. Now as we progressing within technology and new trends and technologies, we would typically find that the system unit are becoming smaller and smaller, and in some instances this can actually nowadays be built into a computer screen. So you don't really see the full system unit that we had before. But with your old traditional desktop computers, you would have seen a big box which was your computer, and inside that computer you had various functions or components and then various devices connected to that computer. So the name of that unit is known as a system unit. What do we find within the system unit? We're going to find memory, we're going to find a processor, or also known as a CPU, the central processing unit. You're also going to find storage devices, hard disks. Connected to your system unit, in this case, we might have a computer screen connected, as well as a keyboard and a mouse. So let's continue and talk about the various components. Now this is where it's going to become a little more technical. When we talk about the system unit and the hardware components, we need to realize that in order for the system unit to function, we need to have various components in place. So the first things we have is we've got input devices, typically in the form of a keyboard, a mouse, and any other peripheral devices. We've got output devices, again in the form of monitors, printers, and other devices such as speakers, earphones, etc. And then you might have external secondary storage, which nowadays we find that we've got external hard disks. So you've got a portable hard disk, you've got memory sticks, USB sticks, and these can be connected to a computing system. If we look at the inside of the system unit, more important, we find the motherboard. Now connected on the motherboard, we will find the CPU, the processor, and the processor is created out of the ALU, and unfortunately there is a lot of abbreviations with this chapter, but as we go on I'm going to explain each of them to you. So the ALU are known as the arithmetic and logical unit. We've got the control unit and we've got registers. The meaning of this will be explained in subsequent slides. Now your CPU communicates with memory. Now memory can be divided into two segments. Primary storage, which will be your RAM and your ROM, and again we're going to come back to this later on. Random access memory or read-only memory. The other type of memory we've mentioned already, this is known as your secondary storage. So this is more permanent, whereas these ones are perhaps more volatile, and usually if you switch off a computer and you haven't saved, your contents is lost. Other components that we find, on your motherboard you're going to find a bus, and the bus is physically a medium that sends the signals from one component to another component. You're going to find various ports, and these ports allow you to connect input devices to the motherboard. So the port is your interface between the actual hardware device and the computer. So your input devices will be connected to ports, your output devices will be connected to ports, as well as all secondary storage devices, typically in the form of USB ports, ports for your external hard disks. So communication takes place between all of these components. Now let's start to look at the meaning of each one of these individual components in a little more detail. So we're going to start off with the CPU. The CPU we said was made up of three components: the ALU, the arithmetic logic unit, the control unit, and registers. Each one of these components has a specific task and objective that they need to adhere to. Now, just for interest's sake, this is typically what a CPU looks like. So it's a small, roughly 5 centimeters by 5 centimeters device or component that would be slotted into the motherboard, which will do all the processing of your computer. So these three units are contained within your CPU. Now if we look at the first one, the arithmetic logic unit, the ALU, this section of the CPU performs all the mathematical calculations and logical comparisons. For example, if you want to add up values, it goes to the ALU. When you're working, let's say you're comparing documents, it should compare values and instructions. Again, it will take place within the ALU. The control unit will allow you to sequentially go and access program instructions. So this one has a few instructions on its own. Okay, so it's going to first of all access the instructions. The second step is it's going to decode them. It's also going to coordinate the flow of data in and out of the ALU, the registers, as well as primary and secondary storage, as well as other devices. So the control unit, we can almost say it's like the traffic cop. It's going to direct traffic to wherever it's supposed to go. The last unit that we find in the CPU is known as registers. Now these are high-speed storage areas that for a small period hold your units of program instructions and your data. So it's sent immediately before and during execution to the registers into the CPU. And from there onwards it's passed to the control unit in ALU. So we're going to see some examples of that a little later on. Now let's go to the next set of components, the bus. The bus can be defined as the physical connections that allow us to share hardware components and that allows communication between hardware components. So within the computer system, it's typically where you see these cables. So cables link up various components or various sections within your motherboard to each other. On this slide or this picture here, we actually see the bottom section of a motherboard. So all of these connections here can also be referred to as the bus, because this would allow certain sections on your motherboard to communicate with other sections. For interest's sake, at the bottom part here, we've got what looks like memory chips, and these memory chips are linked with cables, and these cables have individual wires inside of them. If you look at this one, there's about, if I remember correctly, about 24 more wires, and that allows you to perhaps connect that part of the motherboard to your hard disk or to other sections. If we look at the next slide, this is a better picture of a CPU, or not a CPU, sorry, a motherboard. So if you look at it at the bottom, you see all the different connections and resistors and transistors that's available. Typically in the center here, this is what the CPU location would be like, and then there's various other chips. Now let's continue with the other sections of our system unit. Now first of all, we said, okay, what's a system unit? The system unit is the containment box or the area that's going to contain your motherboard and various components that allows your computer to function, such as a power supply, perhaps an internal hard disk, your memory chips, peripheral cards if it's a desktop computer, etc. So it's going to house all the components responsible for processing. The next term that we need to talk about is primary storage. Now primary storage can also be referred to as main memory or memory, and this is where your instructions are kept while the CPU is busy with processing. Now what we see here, this is a typical example of memory. So if you go to a store and you buy memory, you usually get it, let's say for argument's sake, as 2 megabytes, 4 megabytes, 8 megabytes, 16 megabytes. It actually nowadays goes up to gigabytes. So that indicates the amount of memory available in the computer and pretty much how many instructions per second can be executed by your CPU and saved in memory. Then if we talk about the ports, which allows you to have physical outside devices connected to your motherboard. Some examples that we find. In the older computers nowadays we see less of these. You had your VGA port, which would allow you to connect your computer to a TV or to a data projector. We had S-video connections or ports. These we find less often nowadays. HDMI is the newest standard. So if you buy a new laptop, you would probably see a HDMI port. There are some other video ports. You might find USB ports. You might find your earphone jacks, all those kind of things. So let's go and talk a little more about our processor and how it works with information. Whenever you talk about a computer, people will generally ask you, how fast is your computer? Or if you go to a company and you want to buy one, they will tell you, what speed are you looking for? And the next section actually explains what's going to happen with the processing speed of a computer. Now there's various measures that we need to look at in order to gauge the processing speed. And again, it becomes quite technical, so for those of you that aren't technical, sorry about the following section. So we're going to talk about the clock speed, the machine cycle, as well as some other aspects that influence the processing speed of a computer. So first of all, what is the clock speed? A computer works with electricity, as I'm sure everybody's aware of. And traditionally, if we think about electricity, you either have a signal or a current, or you have no current. So in computing terms, we generally speak about ones and zeros. So when we talk about the clock speed, we are actually referring to the amount of ones and zeros that can be created within a specific time period. So if we look at the definition, it's a series of electronic pulses. Remember, it can either be on or off, a 1 or a 0, at a predetermined rate that affects the machine cycle. So the faster your machine cycle and clock speed, the faster your computer. Now if we go and look at the second bullet, your control unit, as we mentioned, executes an instruction in accordance with the electronic cycle or the clock speed. Each of these instructions will take the exact same time to be executed. For example, if you look at this timeline that we have here, this would indicate that every second one instruction will be executed. So if we look at this one, in 13 seconds we're actually going to have 13 instructions. Now it's not really a second, we're talking here in computing terms about milliseconds. So the faster your computer, the faster instructions can be executed. So how do we measure this? Clock speed is usually measured in multiple gigahertz. For example, nowadays you would see that a laptop or computer has, let's say, 2.3 gigahertz. So you know this amounts to billions of cycles per second. So it's actually very, very fast. The shorter your interval, the faster the execution, the faster your computer, and the more expensive that computer is going to be. However, we are going to be limited by physical constraints. And these constraints actually come in the form of, let me perhaps just go back here. It comes in the form of these connections that we see here. If you look at the bottom of, let's say, this bus, it's going to take a certain amount of time for electricity to move from this point to where it's intended to go to. So unfortunately, we're limited to that. And that's why you would typically find that on most devices or most motherboards, there are actually small golden strands embedded on the motherboard and on the CPU. It has been determined that these conductors actually relay information the quickest. So let's look, what is the current speed of PCs and laptops? So if you go to a store and you see an ad like the following, what does all of this mean? Now first of all, I'm going to jump the gun a bit. There are some components that we haven't discussed, which we will discuss shortly. So what's important here, when we talk about the clock speed or the speed of a computer, you need to look at the gigahertz. So in this case, it's 2.16 gigahertz, meaning we are going to have 2.16 billion instructions or cycles per second. The next thing that you see there, they talk about Intel Celeron, and that just refers to the manufacturer of that particular CPU. The other components, we're not going to spend time on that. We're going to actually come back to that later on. Now, just for interest's sake, what is the highest recorded speed of a computing device? Currently, it is around 5 gigahertz per second. So it's 5 billion instructions per cycle per second. So it's very, very fast, but these computers are going to be extremely expensive. Now let's continue and talk about the machine cycle. What do we mean with a machine cycle? A machine cycle actually consists of 4 steps. Every time that you want to execute an instruction, remember we said we have pulses that takes place, and each one of these will execute an instruction. So when we look at the instruction, it's going to follow the next approach. First of all, the control unit will fetch the instruction from memory. So it's going to receive the instruction. Then it's going to decode the instruction, so it's going to change it into a command that can be recognized. The ALU will take that decoded instruction, it's going to execute the command, and whatever results it obtains, it's going to take those results and save it back into memory. So all of this actually happens within milliseconds. So let's say, for example, we have a small program and we've got 5 instructions. Now this is very simplified, and when you do programming you would realize that it's actually very much more complicated. So let's say, for argument's sake, we want to do the following thing. We want to open a file, we want to locate the first record, we want to make a change to the value, ask the user to make that change, and then we want to update the record and close the file. So each one of these 5 things will go through machine cycles, and these steps will be continuously executed. Now again, just for interest's sake, it's not just going to be 5 instructions, it might be multitude of instructions. So typically something like this could have been thousands of instructions. Let's continue talking about the CPU. Here we find an example of a CPU and what the inner workings look like. So what we find is that there's a bunch of digital circuits imprinted on wafer chips, and these wafer chips are actually what you see in front of you here. So all of these circuits will have the capability to send information from one place to another place. Now just for interest's sake, this is actually real gold. So I don't recommend that you go and break open your computer and try to take it out. It's going to be a very small amount, but this is real gold, which is actually one of the better conductors of electricity. So what do we know? The CPU are going to work with on and off signals, and this is due to the fact that we're working with a circuit board and electricity. So there's either electricity or no electricity. The speed of a CPU can be increased by reducing the length of the digital circuit. So the length that information should travel from one part to another part. But if you think about physics, we can only make it as small as what is allowed by general laws. Okay, so we can't reduce it continuously. So at this stage people are trying to make it more and more effective, but we are reaching our upper limits. Now if you're interested, on YouTube there's actually 2 nice videos where they show you how CPUs are made, the environments in which they generate or create these CPUs, as well as how a CPU works. So it talks about these components that we've mentioned, the ALU, the control unit, the registers, and it shows you how information would move within a CPU. So if you're interested, please go and do so. Now let's go and continue with some other technical aspects. So to recap, we said there's thousands of circuits printed on a silicon chip, and that creates your CPU, and it contains of ones and zeros. Now, when we talk about the information in a computer, the basic unit is actually the ones and zeros, and that's known as a bit. So if we just refer to either a 1 or a 0, that's 1 bit. Now, to work with a computer, we work with combinations of 8 bits. So 8 bits would perhaps represent a number or character or a picture or something. That is also known as a byte. So 8 bits are known as a byte. The next logical unit that we have is kilobytes, and that's 1000 bytes. You guys might be familiar with megabytes. It's a million bytes. Then we have gigabytes, and that's probably where a lot of our cheaper computers currently sit. We are in the range of terabytes. And just for interest's sake, if we talk about the data that's available in the world, we're actually reaching zettabytes. So data, the more storage space you have, the more capability you have for your device, but again, the more expensive it's going to be. So let's move over and talk a little about memory. Memory can be classified as either RAM or ROM, random access memory or read-only memory. Random access memory is the location where all the temporary information and data will be saved. It's also said to be temporary and volatile, meaning that if you switch off electricity, whatever is within RAM will be lost. So you need to actually go and save it on a more physical or dedicated storage location. If we look at the image on the bottom here, sometimes they talk about switches. Now, if you send information into memory, let's say this represents a character A for argument's sake, then it would indicate that that's a 0, 1, 1, 0, 0, 1, 0. And then that would represent a specific character or number. So as information is sent through, it actually sends it as this information. And that makes up the brains of a computer. On the other side, we've got read-only memory. Now, read-only memory is said to be non-volatile, so it's a little more permanent. So if the power goes on, it doesn't disappear. It is more permanent, which would allow you to save data and usually some instructions. And typically we would find that manufacturers would install the basic booting up instructions of a computer in ROM. So every time when you switch on your computer, the instructions that are executed are extracted from ROM, because ROM has the ability to remember that. So it checks whether your screen is on, whether your peripheral devices such as your keyboard and mouse is working, whether it can locate your operating system, and then it goes further. So that's the purpose of ROM. Now let's continue and talk about our processor again. There's some additional terms that we need to look at. Sometimes you might hear that people talk about multiprocessing. Now, multiprocessing is where we've got the simultaneous execution of two or more instructions at the same time. So what we learned up to now with the clock speed and the machine cycle is that it executes one instruction at a particular time. So with multiprocessing, we can actually go and execute multiple instructions. So instead of one, now we can have two, meaning that it makes your computer faster. We also need to understand what is multi-core multiprocessors. Microprocessors can combine two or more independent processors into one. So that's where we have dual-core, quad-core processors. So if you look at this, in this case we've got a processor, and that processor can execute one set of instructions at a time. It needs to wait for instruction to finish before the next one can be executed. If you have two processors combined on that unit, it is typically known as dual-core processors, meaning that it can execute two instructions simultaneously. And this actually goes up to 6-core, 8-core, and already we're seeing 12-core processors. So these are very, very fast computing systems that we typically find. Now again, continuing with processing, we need to know what is the difference between parallel computing, massively parallel computing, and grid computing. Parallel computing is a simultaneous execution of the same task on multiple processors. So if we look at the previous example, in this case we have two tasks or two programs, and these are executed independently. In this case, it gives equal access to each one of the different processors. So that would be parallel computing. Massively parallel computing is environments where we find thousands of processors that are linked together and that operate at the same time. An example of that is typically if you look at what is known as server farms. So companies like Pixar, Walt Disney's, Lucasfilms, whenever they work on new movies and they generate all those CGI special effects, that is too much for one computer for one or quad-core processors. So that would be sent to massively parallel computing environments where the information and the task would be shared amongst hundreds of thousands of processors. The last type of processing that we find is called grid computing. Now with grid computing, we do typically find that people can't necessarily afford all of these processing capabilities by themselves, because we said that the more processing capability you have, the more expensive it's going to be. So what they've done is they've developed a coordinated manner in which people can share their computing resources with each other. So this is a low-cost approach. It can include thousands of computers, and you would typically find that there's a controlling server or computer that will take a task, break it up into subtasks, and that will send it to the independent computers. These computers will perform their small section that they're responsible for. It will send the information back to the controlling computer or server, and that server or computer would combine the results and get a conclusion. Now, who typically uses this? We do find that from time to time, medical institutions, if they want to do statistical analysis, trying to look at new medicines and drugs and stuff, that they need to go and analyze a huge amount of data, and that it's impossible for them to go and do it on single computers. And they would typically share the task, send it for grid computing, and then in the end get a conclusion, and that will be what they're going to use and distribute. Now for the next section, we're actually going to continue and talk about secondary storage, inputs and outputs.